Okay, so what we're learning today is in this unit we've been doing radicals. So today we're going to be graphing radicals and we're going to be graphing shifted radicals. We are going to keep the common theme throughout the year of how we've been graphing functions. We're going to use the parent function's points and then just shift them because we want to stay consistent. So everybody, shifting for all functions works the same, so we don't even have to really learn anything really new today. So we're going to be graphing shifted square root and cube root functions. So first of all, the a times in front of the square root is a stretch or a compression. If a is greater than 1, a stretch. If a is less than 1, it's a vertical compression, right? Grouped in with x is your shift left and right. We go opposite. Added on the outside of the function is our shift up and down, and our sign will stay the same. Now a negative in front of a is a reflection over the x-axis. So you might want to write that down. Oopsies. Reflect over the x-axis. Now a negative in front of x is a reflection over the y-axis. And then just a reminder, if we have a negative in the front, we've got to factor it out, not out of the root, but out of the terms, because that's really actually x plus h. If we factor out a -1, so it's a shift of left h. So just a reminder of that. So we're just going to take these parent functions and transform them. You will have graphs on the back of your worksheet. This is the work I need to be seeing. Okay, so this is how we're going to do it, guys. Let's look at the parent function of f of x is equal to the square root of x. We've got to be able to see how we get these points. Can I plug in a -1?
No.
No, so I'm going to start with 0, correct? Square root of 0 is 0. Square root of 1 is 1. I'm picking whole number points. Square root of 2 is a decimal. I'm not going to choose that one. Square root of 3, square root of 4. Do you see why I'm picking 4? So 2, and then the next one will be 9. The square root of 9 is 3. So watch me graphing those. 0, 0, over 1 up 1, over 4 up 2, over 9 up 3 units. It looks like this.
Oh wait, it's going to go on first step.
Yep, so that's what our square root functions always look like. So with that being said, what is our domain? 0 to infinity, including 0. And then our range is 0 to infinity. Now what we're going to do is just start shifting this bad boy around, shifting it over and down, and that will just affect our domain and range, right, everybody? And it's really easy, and then we can stretch it out. That just means it will grow quicker up, or compress it down. It doesn't grow so quick. Pretty easy, but what we're going to do is we're going to take these points and we're going to transform them. So let's look at our first example. You probably won't need to take notes for this part, but because you'll be able to practice a ton on your own. So looking, just watching, so this would be a right 3 shift, up 2. Do you agree? Now look, what you would do is, you're not going to be given these points. So I would say, the parent function for this is the square root of x. Now where am I getting these points? Plugging in values, just like we just did. Because I keep having people ask me, where are you getting that? Does everybody see why? Now from there, we're shifting right 3, so we'll add 3 to our x's, and then up 2. So we'll add 2 to our y's. So now our new x's are 3, 4, 7, and 9, 10, 11, 12. And then we get a 2, 3. Do you see how I'm adding? Sorry, I lost track. 4, and then 5. So watch me graph that. Now look, our starting point used to be at 0, 0. It's now at 3, 2. Over 3, 2 is my starting point. So be really careful and keep that in mind. Over 4 up 3 units. Over 7 up 4 units. And isn't that all that fits? Now I have people like this and they graph down. Did it? No.
No.
This was starting, so that's where it goes. So now my domain is 3 to infinity. Now look, how could we have determined that without the graph? Right 3, if it used to be at 0 to infinity, do you see how it's 3 to infinity based on the equation? Now, our range is 2 to infinity. And look, because I shifted up 2, that would make sense. Because it hits right on there, right? We can plug in 3 for sure, so it's included in the domain. Okay, awesome. Let's do another one. So looking at this one, hold on. Let me shrink this down so I can write the, in words describe the shift. I need more room for it. Okay, so left 1, correct? Down 3. And then a stretch of 2. And then a reflection, that's its own transformation though, right?
Oh, right.
So that's a reflect over the x-axis. So just a reminder, think about this. If we have a square root function that looks like this, and we stretch it out by 2, it's a vertical stretch. That only affects your y values, not your x values. And then because it's a reflection over the x, that would take something that looks like this and reflect it down here. So that would only change your y values. So we're going to first go to our y values, and we're going to times them by -2. Does everybody see? Because a stretch and a reflection over the x only affects your y values. Then since we're doing left 1, we'll subtract 1 from x. And then after we times by -2, we're then shifting it down 3 units. So then subtracting 3. So then subtracting 1 from all my x's, I get -1, 0, 3, 8. And then 0 times -2 is 0, minus 3 is -3. There's my new starting point. 1 times -2, minus 3. And then 2 times -2, -4 minus 3 is -7, right? 3 times -2, -6 minus 3 is -9. So -1 down 1, 2, 3 units, over 0 down 5 units, over 3 down 7 units, and then over 8 down 9 units. So I'm not going to go over here, am I? Wasn't this a starting? So then it's going to come down and point that way. So now our domain is, the shift was left 1, so it'll be -1 to infinity. Now our range is going to be a little different. Since it's reflected, it's going down to -infinity now. So -infinity up to -3, because it was down 3. Does everybody see? Okay, cool. All right. I think we're probably good with this one, but let's just make sure that everybody would be confident in how to tackle this one. First of all, isn't this a reflection over the y-axis? Reflect over the y-axis. Then also it's a shift of what?
3 to the right. No, left.
So yeah, we would have to make sure we pull out the -1, and then left would be x plus 3, wouldn't it?
Okay.
So left 3. Now, okay, so here's my parent function points, which I get from the square root of x. So a reflection over the y-axis would change your x's, right? If I have a point right here, guys, and I reflect it over the x-axis. Sorry, the y-axis. Isn't your y still up there too? It just changed your x's. So you're going to times your x's by -1, and then you're shifting left 3 after that. So then you would subtract 3. My y's didn't change in this one, right? So let's just do the domain and range on this then. Picture how this graph is going to look. Isn't it going to point back like this?
Yeah.
It was like this. So it must be pointing that way, right?
Yep.
Okay, so my domain is actually -infinity up to
3.
-3, And then our range, isn't it still pointing up though? So our range is, there was no shift up or down, so 0 to infinity. Okay, good. But guys, our new xy points, our y's wouldn't change, right? Our x's would be different. Are we good with me not graphing that one? Okay. All right, looking at this here, it says, solve the radical equation by hand and by calculator. I'm going to do it by hand first, and then I'll just show you how you can kind of do it in the calculator too. So first of all, isolate the radical, done. Then you would square both sides, right? So then we have x minus 2 equals 1, therefore x equals 3. What is a requirement when solving a radical equation? To check your answers for extraneous solutions. That's super important. That's the point of this part, okay? So we have the square root of 3 minus 2 equals 1. The square root of 1 equals 1. 1 equals 1. That is true, so that is not extraneous. So looking at solving this one, we would square both sides, wouldn't we? So we would have x plus 3 equals -x plus 3. So now solving for x, we'd add x, wouldn't we? 2x plus 3 equals 3. So then we'd subtract 3. 2x equals 0. So x equals 0. Let's see if it's extraneous. We have the square root of 0 plus 3. Does that equal the square root of -0 plus 3?
Yes.
Root 3 equals root 3. Yeah, that's the same thing, right? So that is not extraneous. You're going to see this next one happens to be extraneous when we check it. So we'd square both sides, or maybe it just doesn't work. Let's see. So we have x plus 3 equals x minus 2. So then combining our x's, subtract x.
You've got no x's.
So 3 equals negative 2. Is that a true statement?
No.
No. So my answer is
No
no solution. So what if I would have got a true statement, like 3 equals 3? The answer would be
3.
all real numbers, right? We can plug in anything and it will work. So what does this mean, guys? Let me show you here. So let me show you how you could check your answers. Everybody go to your graph. On your calculator, hit y equals. We want to know, when does this square root function equal the function of 1? Because they're both technically functions. So you go to y equals and then type in the square root of x minus 2 in y1. And then in y2, we'll type in 1. We want to know when these are equal. So look, I hit graph. Here's my square root function. And here's my straight line at 1. Now, are we looking for the x value of where they intersect? That would be solving it. So if you count over 1, 2, 3, that's where it intersects. But how I can do it for sure is go like this. Second trace, intersect. So that's number 5. And then first curve, just make sure you can actually see an xy point on the first curve, because people's calculators were having some weirdness going on. So hit enter. Second curve, hit enter. And it says, do you want me to guess? The intersection is at x equals 3, and it would be up at 1. Which makes sense, right? If we have a straight line at 1, it's going to be up at 1. Okay, so we just solved it by hand. So what do you think, since this one is no solution, what must be happening with our graphs? They don't ever cross. Well, one looks like this, and one looks like this. So do you see how that would make sense? Because they never cross. Okay. So you can really do it by hand as long as you, if it's a solved by calculator, you can do it by hand, but you got to check your answers. All right. Let's look at some cube root functions, and then we're all done, pretty much. So, a cube root of x is the parent function with no shifts. So if I was to plug in points, just a reminder, for an odd root, can we plug in any number? Negatives, positives? Yeah. So let's pick perfect cubes, like negative 8. The cube root of negative 8 is negative 2, isn't it? And then the cube root of negative 1, isn't that the next one? Cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. So graphing that, negative 8, negative 2 units, over negative 1, 0, 0, over 1 up 1, over 8 up 2. It's a cube root is like this S-looking thing. That's what a cube root function looks like. So our domain, if we can plug anything into our domain, it's all real numbers, correct? Well, it's pointing left and right forever. So our domain is all real numbers, or negative infinity to infinity. Well, our range, isn't it also pointing down and up forever? So our range is also all real numbers. Now picture me shifting this graph around, moving it. Will that change the fact that it's pointing left and right forever? No, and it will not change the fact it's pointing down and up forever. For all cube roots, domain and range, no matter what, are always all real numbers. So those are easy to find. So now let's just do maybe one example of such. So let's just go right to this wall. It doesn't matter. Okay, so in Word you would say left 1, down 3 units. So you'd say, here are my parent function points from the cube root of x. People ask me where I get them. I plugged in values, right? You guys see what I'm doing? Everybody? Okay, so then from there we're going to shift left 1, so subtract 1, and then down 3, subtract 3. So now we have negative 9, negative 2, negative 1, 0, 7. Negative 2 minus 3 is negative 5, negative 4, negative 3, negative 2, and then it looks like negative 1, right? Subtracting 3. Okay, so negative 9, negative 5 units, negative 2, negative 4, negative 1, negative 3, over 0, down 2, and then over 7, down 1. So it's an S. I can see it, how it's connecting. There it is. Domain and range, all real numbers, all real numbers. Sweet. Okay, awesome. So on this one, this would be a stretch and reflection over the x, correct? So we would times all of our x values by, or would I times my y values?
Y values.
Times my y values by negative 2, and then we would, after that, subtract 5 from x. And we get the picture here. Do you agree?
Yes.
Okay. lesson. Okay, so determine the shift from the parent function. Now looking at this, there's a problem. We can't determine the shift because of what reason? Can anyone tell me what's weird? The 4. Instead of just x, it's a 4. So can anyone give me a suggestion to get it just to an x? Pull out the 4. Now you don't mean pull it out because it's under, right? But you mean pull it out of the terms. Yeah, I just wanted you to be more specific. So we have the square root, we'll pull it out. So then divide by 4, divide by 4. So then left is x minus 1, isn't it?
Yeah.
Plus 1. Now remember, because it's multiplication, we can split it up.
So it would be 2, so then it would be 6.
Good, yep. So we have this and this are the same thing, right? So he's saying the square root of 4 is 2. 2 times 3 is? So we have 6 square roots of x minus 1 plus 1. So now in words, our shift is right 1, up 1, and a stretch of 6. Is everybody good with that? So let's just, without that, let's do our domain. It was right 1. So our domain would be 1 to infinity, wouldn't it? Now our range is up 1. It's stretched out 6, but that's not changing. It's just going up quicker. So our range would be 1 to infinity. Okay, good. All right, next one, what do I factor out?
16.
And then left is x minus 2. So negative 4 square roots of x minus 2.
Yeah.
So then right 2, stretch of 4.
And a reflection over the x-axis.
Okay, let's do domain and range. So careful here, since it's reflected over x, that
It's going to be negative.
our range is going to be negative, but our domain will stay the same, won't it? So right 2, so that means 2 to infinity. And since it's reflected, it's pointing down, so it'll be negative infinity up to, was there any shift up or down?
Nope. 0.
0. Okay, good. Okay, so same idea with cube roots. It would make sense that on this example, what do we have to pull out, even though it doesn't seem like the best?
2.
Well, we have to make it a 1. So no matter what, we have to pull out an 8, everybody. Do you see? Even if it doesn't divide very pretty. So we have this, 3 minus the cube root of 8. So when I divide by 8, do you see how I get x minus a half? Well, that's okay. So then we have 3 minus 2, the cube root of 8 is 2, and then we have the cube root of x minus a half. So now this 3 is just out in front. Shouldn't I just probably go plus 3 back here?
Yeah.
Same thing, right? Don't combine those two. They're not together.
So it would be
So you'd say right a half, up 3,
3,
stretch a 2, and a reflection over the x. Domain and range for all cube root functions. All real numbers. Okay. So I think we get the picture with that. Okay. We factor out a negative 27, right? Okay.
So it has to come up.
Right. All right, that's the end of the lesson. The rest of the time is yours. Don't wait.